No, this is the question. Done. Yes, what is the answer? Yes, see, the question is 2.8 gram of N2 gas at 300 Kelvin and 20 atmospheric was allowed to expand isothermally against a constant external pressure, that is 1 atmospheric. Okay. So obviously when expansion is there, so volume will increase, correct? Could you tell me what is the initial volume? P1 V1 is equals to N1 RT1, we can write. Initial condition is this, right? So initial volume is, you can substitute all the values here. Number of moles would be 2.8 divided by 28. R is 0.0821. Temperature is 300 Kelvin. And this entire thing is divided by the pressure, which is 20 atmospheric. Initially it is given. When you solve this, you'll get initial volume, and initial volume is 0.123 liter. You will get that approximately. Now, when the expansion is there against this pressure, so again we can write P2 V2 is equals to N2 RT2. nRT is same, it is not changing. So volume, final volume would be 2.8 divided by 28 into 0.0821 into 300, and this whole thing is divided by 20. Sorry, 1 atmospheric. Okay, pressure is 1 atmospheric. So when you solve this, you'll get volume, and the volume is 2.463 liter. Okay, so this is the expansion, the change in volume. So what is the work done in this process? Could you tell me? Work done is minus P external into delta V. Minus P external we have, that is 1. Delta V is 2.463 minus 0.123. This is a change in volume we have. So when you solve this, again you will get minus 2340 atm liter, which again you can convert it into joule, and that would be minus 236.95 joule approximately. Okay, we need to find out delta U. Since the question it is given that it is an isothermal process. So delta U for isothermal process is, we know it is 0 for isothermal process, and then we can find out delta Q, it is expansion, so work done by the system. Okay, so Q is equals to, or delta U is equals to Q plus W, we can write, we can substitute the value. So Q is equals to plus 236.95 joule. Understood? So this is how we find out the thing. So expansion was there, all conditions were given. V1, V2 will find out first. Once you have V1, V2, you have pressure, you can find out work done, and then delta U, isothermal process 0, and hence Q we can find out using first law of thermodynamics. Okay, now when you have PV graph given, okay, then the work done would be what? Area under curve, that you know. Okay, so look at this question here. This is, suppose, volume V, or I'll give you some value, just a second. This is 2, 4, 6, and this is 8. This is volume given in liter. 1, 2, 3, 4, pressure in ATM. Right? The process is A to B. C, D, and A. You need to find out work done in this process, total work done. Minus 18 you are getting, right? So we'll find out the area under curve, right? So work done in PV graph is nothing but area under the curve. Only in PV graph it is. Only in PV graph, area under curve. So what is the area here? Length into breadth, right? Rectangle. So length is 6 and breadth is 4, right? Sorry, 3. So area is nothing but the work done. So area is, we have 3 into 6. So we have 18. Okay. Unit is ATM liter here, which you can convert in joule if you want easily. Okay. ATM liter. But so the next is here, you see, work done total, area though you can find out simply, but total work done would be what? If you see whether it is negative or positive, then what we'll do? We'll have work done in A to B plus work done in B to C plus work done in C to D plus work done in D to A. This is the entire thing. So B to C and D to A, you see it is a constant volume process. So work done would be 0 here in these two processes. Constant volume. A to B and C to D, you see, the expansion is taking place against the constant pressure 4. So minus 4 into change in volume is 6 plus. This is 0. This would be C to D. We have compression against 1. So minus 1 into 2 minus 8, that is minus 6. So minus 24 plus 6, we are getting minus 18 ATM liter. So when you solve like this stepwise, you will get the sign, okay, whether it is negative or positive. But area under the curve, if you find out, then we'll have only the magnitude, not the sign. Okay. Minus 4 into delta V, no? So 8 minus this, 8 minus 2, 6. 6 into 4 is 24. Work done formula is minus P external into delta V. In the formula itself, we have minus P. Minus P external into delta V. Correct. So here you'll get the sign. And this sign means the work done by the system because it is negative. So work done by the system. Okay, work done by the system. So what happens here? We have 18 ATM liter Okay. Whenever you have clockwise process, right? You see, it's clockwise, correct? Clockwise. So when the cyclic process is clockwise, then it is always work done by the system. So what you do, area you find out, you'll get the magnitude. And then since the process is clockwise, so you have to put a negative sign over here. Okay, and that is what the answer is. So what is the final conclusion here? If clockwise process is there, if the process is clockwise, then it is work done by the system. Work done by the system. If process is anti-clockwise, work done on the system. Right? These two things you have to keep in mind. Okay. Whenever you have graph, PV graph, find out area. If it is clockwise, put a negative sign. If it is anti-clockwise, put a positive sign over there, and that is it. Understood? Clear? Okay. Okay, can we move on? Next. So this kind of questions you will see. Clockwise, anti-clockwise process you must remember. Now the next is next term you write down enthalpy. Represented by H. Okay. Mathematically, H is defined as the sum of internal energy and pressure volume work done. Sum of internal energy and pressure volume work done. Correct? Mathematically, it is defined like this. It is also defined as the heat content. Enthalpy is the heat content of system at constant pressure. Heat content of the system at constant pressure. So if you look at this expression here, of FLOT, first law of thermodynamics, du is equals to dq plus dw. Okay, so this is equals to dq. dw we can write minus dpv. So this is equals to dq plus minus pdv plus vdp, pdv plus vdp. Okay, when the pressure is constant, because our condition is what? Constant pressure. At constant pressure, what happens? This term would be 0. Okay, so what we can write here, you see, du is equals to dq plus, sorry, minus pdv at constant pressure. At constant pressure. Okay, so what is dq here? dq is equals to du plus pdv, and that is what we have here. If you see this expression, du is equals to du plus pdv is nothing but dh. If you see here, dh is equals to du plus pdv at constant pressure. So here, if I write down one more steps, if I write down here, at constant pressure, dh is equals to du plus p. So this is dh, and this is nothing but dq over here. So from the first, these two expression, what we can write? dq, the heat at constant pressure is nothing but dh. So this is what the mathematical definition of enthalpy we have. It is the heat content of the system at constant pressure. Okay, done. Clear? Done, guys. Copied. Okay. Now you see, like we did for internal energy, enthalpy also, yes, H is the enthalpy, and it is also the function of last part. Okay, the last part. Second last step. Second last step is nothing. We just see dq is what? Du plus pdv, and du plus pdv from this expression is nothing but dh. So dh and dq we can equate these two. That's what we did here. That's why the enthalpy is nothing but the heat content of the system at constant pressure, because all these things we have applied at constant pressure. The condition we have taken at constant pressure, correct? So this is the thing we have. Okay. Now you see enthalpy is the function of pressure and temperature. Is a function of pressure and temperature. It depends on pressure as well as the temperature mainly. Okay, it depends upon the number of moles also and volume also to some extent. But for closed system, the number of moles and volumes are constant. So mainly these two factors we have which affects the enthalpy. So by Euler's theorem, what we can write, dH is equals to again dou H by dou P, differentiation with respect to one variable keeping other constant into dP, plus dou H by dou T keeping P constant dt. Okay, this is the formula we have, correct? Yeah, this is the formula. Now, dou H by dou P at constant temperature, this is Cp. And for n number of moles, you see, dH is equals to n Cp Cp dt plus dou H by dou P at constant temperature dP. Right? This is also true and valid for all the processes. Valid for all kind of process. This is in general formula we have. You must have seen the formula of dH is equals to Ncp dt, isn't it? Have you seen that formula? dH is equals to Ncp dt, right? But this formula is the actual formula of dH for all process. Okay, so it is applicable for all process, and dH is equals to Ncp dt. We'll apply one condition and we'll get that relation. Did you understand till here? Yes, done till here? Okay. Now, condition you seen, this is the expression we get. Now, if you apply the condition for ideal gas here, for ideal gas, we have H is equals to U plus PV. This is the expression we have of enthalpy. U is a function of temperature, internal energy, and PV for ideal gas is nothing but nRT for ideal gas. So this PV also we can say it is a function of temperature. Okay, so overall we can say H is a function of temperature. Right? H is a function of temperature, It means the differentiation of enthalpy with respect to pressure at constant temperature equals to 0. Yes. And this, if you substitute in that general formula, we'll get dH is equals to NCP dt, NCP dt, right? Why? Because this dH, dou H by dou P at constant temperature, we have substituted here in this expression. This entire term is 0 and dH is equals to NCP dt. So when we write this dH is equals to NCP dt, it is valid for ideal gas only. For ideal gas. For ideal gas, all processes. It's not like only constant pressure, all processes, because we did not apply any condition of constant pressure over here. Okay, whether pressure is constant or not, we can apply this. Yes. Clear? Okay. If the pressure is constant, suppose it is given in the question, the pressure is constant, then obviously this expression would be 0. This dp would be 0, and when this dp is 0, the entire expression is 0, and again dH is equals to NCP dt. So it is applicable for constant pressure as well, but at delta H or dH is equals to NCP dt is applicable for all processes. Okay, so this is one thing. Now in chemical reaction, how do we use this expression? You see this. In continuation, you write down for chemical reaction what happens. For chemical reaction, any chemical reaction, it takes place at constant pressure and temperature. Okay, so generally what happens, generally chemical reaction takes place at constant pressure and temperature. Constant pressure and temperature. When you have constant pressure, we know at constant pressure, Q is nothing but the enthalpy, that is delta H. And if the constant volume is there, at constant volume, Q is nothing but the change in internal energy, delta U. Okay, and W, if you see work done, is equals to minus P dV integral. Okay, 2 from initial volume to final volume, Vi to Vf. Okay, initial volume to final volume. So pressure is P dV is what we can write. We can write P dV is nR dt, or nRT we can write, right? So if we can write the NF final number of moles only for gases. This is only for gases, okay? R into T minus Ni initial number of moles only for gases R into T. This we can do. Vf minus Vi is this. So this would be equals to minus one negative sign is already there. So this would be equals to minus NF minus Ni for gases RT, which is equals to minus delta Ng RT. PdV is minus delta Ng RT. Because we are applying PV is equals to nRT here in order to find out the value of PdV. PV is equals to nRT is applicable only for gases. Okay. Correct. So any chemical reaction generally takes place at constant temperature and pressure. This is what the definition of enthalpy or at constant temperature, heat content of the system is nothing but the enthalpy change. Right? So it's not like I got it. I have done it already. I've just written it over here. Q is equals to delta H. Similarly, this also we have done, delta U. Okay. So PdV is equals to delta Ng RT. So the expression of delta H would be for chemical reactions, gaseous species. Delta H is equals to delta U plus delta Ng RT. This is the formula we have. We can use this formula for chemical reaction. Delta Ng will calculate only for gases. Okay. Once again, Shitish. Delta Ng is number of gaseous product minus the number of gaseous reactant. Number of gaseous product and gaseous reactant. Correct? Look at this example here. Suppose we have a reaction that is 3O2 gas gives 2O3 gases. So delta Ng for this reaction would be 2 minus 3. Product minus reactant, that is minus 1. So delta Ng is what? Delta Ng is less than 0 for this reaction. And when delta Ng is less than 0, work done is less than 0. Work done is negative. Work done is negative means It is work done by the system. Is it clear? Because you see, work done is what? This expression you see, work done is minus P delta V, P dV, which is nothing but minus delta Ng RT for gaseous reaction. Delta Ng RT is negative. One second. Okay, one mistake I made. Delta N is negative, no? So negative, negative becomes positive. So work done is positive. Work done is positive means work done on the system we have. One correction. Right? Delta Ng negative. So negative, negative, positive. So work done on the system. Okay, next you see, if you have this reaction, N2 gas plus 3H2 gas gives 2NH3 gas. Okay, so for this, you see delta Ng or the reaction like this, CaCO3, we have solid, gives CaO solid plus CO2 gas. For these reactions, you see delta Ng is greater than 0, right? Delta Ng is greater than 0 means work done is negative. Work done is negative means work done by the system. Okay, when you have negative, it means work done by the system, and when system is doing work, it is a case of expansion. When work done on the system means we are doing work on the system, so it is a case of compression. Done. One note you write down, in case of change in state, in case of change in state, the change in volume delta V is almost zero. There is no change in volume when there's a state change is there. We have one exception in this, that is the melting of ice. In this case, what happens when H2O solid, that is ice, is converting into H2O liquid, right? Ice, what happens in case of ice? In case of ice, we have open cage like structure. Open cage like structure. We have some void, vacant space over there in ice. That's why density is less and it can float on water. Okay, it's open cage like structure. We have some void space present over there. It's not like solid we have from inside, right? And we have, when this ice melts, we have hydrogen bonding present in liquid, right? So due to hydrogen bonding, what happens? Due to hydrogen bonding in water, volume decreases. This is the information sort of things. You should keep this in mind, okay? Usually when there is a change in state, we don't observe much change in volume. Delta V is zero almost, right? But in case of ice and liquid, we have open cage structure. Due to hydrogen bonding in water, volume decreases, and it is a case of compression. It is the case of compression, and compression means work done on the system, right? So it is work done on the system, hence it is positive. Okay, this one information you must remember. See, when there is bonding, right, when there is bonding, there will be a compression, right? Molecules are attracting, no, HOH. These molecules are attracting because of this bonding, right? So usually the kind of expansion that we observe, we don't have in this case. We don't observe the expansion. Actually, we have almost similar volume. Change in volume is not that great, okay? But because of this attraction, hydrogen bonding, we observe some compression in this case, ice to water. And that's why we say it is compression and work done on the system. Clear? Understood? It is not getting compressed. Okay, relatively we are talking about. Means the volume that we are expecting, we don't get the exact same volume, but it is slightly lesser than that. So ice is converting into liquid, but the volume is not that great according to our expectation. That's why we say in this process, there is a sort of a compression we have. It means work is done on the system. when you convert ice to liquid. Okay. So this is for enthalpy and the relation we have. Important relation delta H, delta U, and delta NGRT. Very important relation we have that you must keep that in mind. Now, so we'll take a break now. And after the break, we'll see some more relations here, which is important for the other concept that we are going to see. Fine. So we'll take a break now. We'll resume at 6:30. Okay. Take a break, guys.